Yeah, hello everyone. It's really a great pleasure to be here. SREcon for me is always something special. So exactly 7 years ago, I gave my first talk ever at a conference at SREcon in Europe. It was in Dublin, I think, back then. And the title was the same. So I'm not sure if it's a good thing or a bad thing that I'm still talking about the same things, but it's definitely a topic that I care about a lot. And I hope I got a little bit wiser over the years. I certainly got a lot bigger. So yeah, thanks for coming. And yeah, let's see. I put some information about myself on this slide just to give you a little bit more of a background. So maybe the important takeaway is that I'm by training a mathematician. So in my spare time, I really like to think about mathematics and read some papers. Then 10 years ago, roughly, I went into IT, working for a monitoring vendor. This is also where I started going to conferences like this, talking about statistics. And right now, I'm leading the SRE department for a company called Zalando. Right. I talked about this topic, as Effie alluded to, over the past years quite a bit, and I put some recent talks here as well, so you can follow up on this. This presentation is basically a condensation of a lot of the material that was found in such talks, and I try to compress it to the most interesting parts, the most entertaining parts, and I actually removed a lot of the mathematical slides. So I think yesterday when I was trying to squeeze out another minute, I removed the last formula from it. So it will be still a lot of statistics, a lot of topics to cover, and without further ado, let me just dive into it. So for statistics, I will not be talking about machine learning or anything fancy. We will start with the very basics, and visualizations are always the first thing. If you are presented with a new data set, it's important to know how to visualize it. And I will use these slides to give you an idea about different visualizations, so we are kind of primed to recognize them further along, and also present you some of the data sets. So the first one, it's like, if you are talking about statistics and not have a slide with a normal distribution, I think you're also doing something wrong. So that is how it looks like. It's mainly example how operations data does not normally look like. But yeah, we can still use it to familiarize ourselves with these visualizations. So the first one you see at the top, it's called a rug plot. It's just like for every data point you have in a data set, you are putting I think it's called a rug, but it's essentially just a line at the x-axis. So it's a very, very fair representation. You see, one of the issues with that visualizations right away, it can get crowded quite a bit. So this is 1,000 samples, which isn't actually that much, and it's already quite dense. So a second way to visualize just raw data is then a histogram. I think probably all of you have seen histograms before. Just real quick, what you do to produce a histogram is you choose a binning of your x-axis, which are just a number of values, and then with everything that falls between two of those values, you count how many data points lie in there. And you see, you can judge the shades of the kind of mess in the middle in the rug plot by looking at it with a histogram. One interesting observation about histograms is that the area is proportional to the count. So areas are something that the eye is very good at recognizing. So with the histograms, you kind of have that ability to quickly grasp how many samples there are. And with telemetry data, you usually have a time dependence, or actually always have some kind of timestamps you're recording with it. So putting that time in the x-axis is also very, very natural. If you do that with normal distributed random samples, then you get a chart like that, which looks like noise. So it's called white noise. Here's a graph that you will be more familiar with. So the last one is certainly a thing that you see in all your dashboards. It's a request rate chart. All these data sets are taken from production. There's also a GitHub repository. We can download it and play around with it yourself. That's just very simple. 3 requests days or days of request rates. And yeah, I always like to put the dots on the line charts because those are the actual measurements. The lines in between doesn't really mean a lot. For this one, it's kind of defensible. For others, not so much. And how do you get the other two representations? Well, you forgot about the time dimension. So you get rid of the x-axis, project everything to the y-axis, and then you are left with a rug plot. So those would be kind of dots showing on this axis here. And if you rotate it, then we get the rug plot. And the histogram is again what the histogram is. Now we come to like my most favorite data set ever, which is request latencies, and I will talk about latencies quite a bit. And this is, from a statistical perspective, the most exciting data that we have in the monitoring space, at least for me. So again, we see how the rug plot looks like. Top here, there's a lot of crowded stuff going on. In the histogram, you have more of an idea. And then looking at the time-dependent representation, you kind of see the main mode corresponding to these values here at the bottom. And then there's actually quite some outliers scattered on the top. And you see some structure here in the histogram. You can see multiple modes. These are kind of called this local maxima. You can also see it in the rug plots. And then you have like further outliers down here. Note that this is capped at 100, and this is capped at 1,200. So always, if we are looking at this kind of latency charts, there's usually a long, long tail which is hidden. Just like sometimes the query just took an hour, and it's like far out. It's really a challenge to visualize this. So here's a very similar data set because latency also not comes just as a global thing, but also something that depends on time. And if you are chopping a day into 24 hours and produce this kind of aggregates for each hour, then this is what you arrive at. This will be a data set that we look at quite a bit. So I want to bring your attention to the different crowdedness of this graph. So in this kind of chart, you have 80 requests. That's all there is. Here's 100. There's 25. And here is like 90K, close to 100K, 108K. So your service is loaded over time or maybe loaded over time very differently, so you get very different numbers of samples. Same data set again. So this is how it looks like when you draw histograms. The histograms with lots of samples are very smooth. The histograms with very little samples are like spiky and spotty, and they resemble a rug plot to a certain degree. Now, a challenge that you have with that is if you want to put that time again on an x-axis, you usually don't look at charts like that in your monitoring system. You don't have this kind of visualization. So you kind of want to compress it and make the time on the x-axis again, and we kind of have a dimension to less. We kind of spent already 2 dimensions on the full histogram, and this rug plot is not very good at messing around with these dense areas. And there's another trick we can apply, is we use color as the 3rd dimension. So the density will be encoded in dark colors. This is what we call a heat map. A nice thing you can do with a heat map is you can then use time as an x-axis. Here I just have the 24 hours, and you see the latency distribution here. So this is exactly the same information that I had in this chart, just presented in this way. And this has been a visualization that I was always liking quite a bit, and it's completely awesome to see that over the past years, we are actually seeing this kind of nice visualizations of latency data in our tools. This is a screenshot from the Grafana blog or documentation. They now have this kind of heat map visualization of latency. And Seconus, that's the tool I was working for before, they pioneered a lot of this with their high-resolution histogram views, which give you a very nice overview. So actually, this is exactly the same data set we are looking at here. Here you have a 24-hour view, and here you have a minute-wise summary of what's going on here. So now we come to the statistics part of it, having just looked at the data, which is arguably already statistics, but I want to talk about statistics. So statistics and aggregates are extremely important for telemetry applications. They are completely prevalent. So you want to aggregate telemetry data across time, in graphs, across hosts or endpoints. So every time you're forgetting about some aggregates, you are already talking about aggregations, and you need to know what different aggregates you have. And the first one is the average. I think everybody knows already what the average is. I don't know how many could produce the formula, but I think a good part of you would be able to. Intuitively, we think about averages as the point of support. So if I put my rugs in a physical model and put it on a weightless bar, then the point of support of that bar that it's in equilibrium would be the mean. So you can see how that works out. This is, I didn't calculate it, but they kind of looked right. So by your intuition, it's like if a lot of heavy stuff is there, and then you have some stuff over here, then the average is over here. And there's one phenomenon called leverage. If this guy moves out a lot to this side, then you can actually balance a lot of things on the other side. The way to rephrase that in other words is that the mean value is not robust. So if you were forgetting about this sample, the mean value would be here. And if you're adding just one sample, which may be arbitrarily far away, your mean value can change in unbounded ways. So by just adding one sample, I can put the mean value very far away. So that's just like non-robustness. You can have a single sample which is disturbing your mean value. And so let's look at the data sets we came before. Normal distribution, it's again just so beautiful, everything works out. Mean value is right in the middle, this is how it was designed. Request rates, mean values for request rates do make a lot of sense. I think we all have heard of the average request rate over a day or something like that. That's actually also a sensible way to look at requests. And then for latency, we see some of this leverage thing going on. You have kind of the bulk of your distribution here, and the average is shifted out. And that's exactly because we have samples which are just very far to kind of press the lever down with some weight. So that's going on. So this is kind of a quiz. We don't have time to do the real quiz, so I'm just doing the quiz for you, just to demonstrate where averages are, because averages are literally everywhere. So every graph we look at has some averages in it. So the question is, where is actually the average? Let me ask you differently. What is the max RPS you see in that chart? And just now looking at it, I'm just like, here it is. I'm going to that axis, like 6.5. So it looks like max RPS is 6.5. Turns out max XPS is actually 14, and it was attained here. So what happened? Actually, this is a full month of data. How many minutes are in a full month? Turns out like 1,400 a day, that's a number I can remember, times 30, it's about 40K. It's 40,000 numbers that are collected over 1 month, and you only have 500 little dots you painted. So this is every chart you're looking at, if you're zooming out, is really a group by with some aggregation applied to it. So you all the time have this question, which aggregation is chosen? By default, most tools use the average, and then you just have average request rates here about hours, and you don't have the max. So SREcon has this nice feature where you can overlay different aggregations, so max, average, and min. Also in Grafana, I've seen it with some adapters that you can do it. Just something to be aware of. You always, if you are zooming or looking at graphs, you have some implicit aggregation going on. And this phenomenon, you zoom into graphs and the spikes get larger, or you zoom out of graphs and the spikes get lower. I call it spike erosion. I found that a good name, so watch out for that. With request latencies, the situation with mean values is actually completely terrible. So we already saw some examples where it wasn't exactly looking great, but look at this graph, for example, with this 100,000 samples. Like this average is nowhere close to the body of the distribution. And I overlaid it here as kind of a graph. So you may be seeing mean latency graphs. So 10 years ago, I think people were plotting this. I have not seen that in any tool for a long time. So nobody looks at mean values. And there's also a very nice quote that I want to quote Dogan Urulugu from Optimizely, who says, looking at your average latency is like measuring the average top temperature of your hospital. Yeah, like my station has 38.5 degrees average. Like, great. Do we have a problem? No way to tell we have a problem. And the good thing about temperatures in hospital is that the temperature is bounded. You die if you are like over 42. And with latency, it's not the case. So it's even worse than looking at the temperatures in the hospital. So don't do it. Wrapping up, most data we've seen is averaged. So be aware of the spike erosion thingy. Averages are easy to compute and mergeable. I'm not talking about that too much here. And don't do average latency. It's not good. So the median is a second similar thing like the average, which gives you robustness. So the idea is similar to the average. We kind of trying to find a sample representative, but we do it in a different way this time. And I gave you a simple example here. You have 178 values here and 178 values there. You can maybe later count if this is really 178. But it's the same number. That's the important thing. And then you have one single guy in the middle. And this is, if it looks like that, then that certainly is the median. And you kind of, if you don't have that guy in the middle and you don't really know where the median is, so yeah, you have to make a choice. And there's not so much surprising things going on. The mathematician will say, well, a median value is a value which divides the data set into equal halves. So you have a kind of a median range of multiple median values. But the practical choice is like everybody chooses the middle here. So there's really no issue. Looking at the data sets again, request rates, normal noise looks exactly like the average. And here for the request latency, we have kind of solved our leverage problem here. This guy stays right in the middle. The few outliers cannot harm it much, and you see this all over these charts again. Here it's in the middle, there's in the middle. It really gives you where the body of the distribution is. And this is also what you see here. Like, this is really 50% of the data is below, 50% is on the top, so you get that. It's just what it is, just like half of it. You may not care just about half of your population of requests, but this is at least what you can clearly get with this. There's one thing I didn't talk about much about this kind of empty space in the middle. There's actually quite some data there. It's like the color coding is not able to have enough fidelity. So here it's like 90,000, here's 100. So it kind of looks empty, but there is some data. It's just not showing up in the plot. So wrapping this up real quick. So medians gives us central representatives. We have seen that kind of how they are central choices. They are robust to outliers. So if you have a single outlier somewhere, the median does not move much. We have seen that in the graph. And then fact, medians are not easily mergeable. So what do I mean by this? In operations, we are actually oftentimes confronted with multiple stages of aggregation. You maybe have several nodes where you are calculating some numbers, and then you want to further aggregate them on top. Or you may have some Kubernetes clusters where you do pre-aggregation, some like pieces of infrastructure like laying there you want to aggregate. So it's often very important that you are able to do a multi-step aggregation. Also, if you have time-wise aggregation, you maybe have data over an hour and then you want to go to a month. How do you aggregate further? So it's often like a very important aspect of a statistic, is it mergeable? I already told you that averages are mergeable. This shouldn't be surprising. Median values are actually not easily mergeable, or actually not mergeable. So if you just retain the median, then you have no way to know what the median of the aggregation was. And we'll talk about, in the context of percentiles, we'll talk about this more. Jumping right in, here's the percentile thing. You will recognize the pattern. If you have a data set like that, 90 values here, 10 values here, one single value here, then we all agree what a P90 is. This is the P90. So basic idea being, the Px is like X% of the values are below, and the 100 minus X% are here. So a P10 would be 10% here, 90% there. P50 is 50% here, 50% there. And you will all be recognizing, well, 3 of them I already know. So P0, everything on one side is a minimum. P100, everything on the other side is a maximum. And yeah, the median is exactly the same thing that we just saw before. And there's, again, the same question, like, if I don't have that central representative here, where does it go? So in this case, it's actually a quite subtle one. We don't have one single that everybody agrees on, but actually nobody agrees on what's the right one to pick. There are a big paper from 1996, which already found like 7 or 8 different versions. Wikipedia now lists 9. Nobody agrees what the true percentile is. The good thing is you usually don't have to care, unless you are benchmarking several percentiles and comparing them. So ask me why I looked into this. But yeah, just there are some hidden demons, but hopefully you will not need to go there. Here's how the P90 look like for the data sets we always talk about. Again, like 90% of the stuff is here, 10% of the stuff is here. So it's a relatively fair thing. Well, actually, I made a mistake here. This is a 99 percentile, not a 90th percentile. I don't really know how that happens, but it's 99% of everything is here, and this is the 1%. Okay, looking at this again, this shows you kind of how it looks like in the settings. It's always the same thing, 90% here, 10% here. Yeah, this is how it looks like. It gives you an idea about the tail of your distribution, which is oftentimes for latency the thing that you're most interested in. And we can also overlay this in the graph. And you kind of see the full distribution again here, and this individual red dots, rugs, became that kind of thing. You see also that if you have little data, the percentiles often get all over the place. So later, if you're maybe zooming out and you are in a situation where you average this out, then it's really a question, what are you even averaging? Right. So in your tools, you oftentimes don't have this kind of heat map or histogram in the background, but you have this kind of percentile graphs. And yeah, so this is how it looks like. This is production data from our Zalando systems. You're probably familiar with this kind of UAT data. So again, I talked about the importance of merging, and there's always the question, can you merge percentiles? And the answer is no. Naively aggregating percentiles with the average doesn't work. In this example we're talking about here, there's a 68% error. And yeah, don't do it. I just want to give you some motivation. I could go on about this, but the basic reason behind this, why you cannot do it, is again because you retain too little information about the distribution. So here I put some data sets which all have the same P90. So you may have 90 values and 10. You may have 90 million values and 10 million values. Yeah, same P90. You may have 90 values all the way here and 10 values very close, or it may be the other way around. So you can imagine if you are merging this kind of things, all kinds of things can happen. And just the P90 gives you very little information about the distribution. So if you want to have mergeable versions where you can do the aggregation and then calculate the percentiles or get accurate percentiles, you need some kind of way to store more information about the distribution. And I have been talking about this topic for a long time, since I was also involved in one of the data structures that is able to do it. So Seconus had the circle hist available as open histogram for a while. That is like allowing you to do this kind of aggregation. But now we have a lot of things to choose from. So HDR histograms, T-digest for things that were preceding the open histogram efforts. Now we have DD sketch, UD sketch, Prometheus sparse histograms, open telemetry histograms, and those are really great technologies to kind of aggregate and merge latency distributions. So that's coming up. One shout I want to make here that this sparse thing is really important. Prometheus has a histogram data type, which is very, very naive. They usually have just 10 buckets or so, and the accuracy of percentiles you get out of it is just very bad, like 300% error in some cases. So be aware of this, but there is hope. Sparse histograms are coming. Sparse histograms are already available in various tools. If you're looking at latency data, care about performance a lot, something to watch out for. So quickly, the takeaways here are percentiles generate min, max, and median. Percentiles are used to describe latencies, and percentile can be aggregated, not be aggregated unless you have histograms. Right, 90% through my time. First half of the presentation is done. But this one is quick. Latency SLOs are actually massive aggregation, time-wise aggregation. So everything we kind of learned about percentile aggregation can be applied here. So here's an SLO, 99% of the requests past 28 steps were served within 100 milliseconds. And what people always do here is look at the P99, right? Because this was here 99% of the requests. So I look at this chart and say, here are the milliseconds, here's the P99. Well, it looks like okay-ish, should be fine, but you can't actually know. There's a possibility that you had a big batch job coming in here where you were just having 90 million requests and they were actually quite slow. And if you are doing the proper aggregate, it might be dominated by this spike. So you just have too little information to decide, and the ways of fixing it are not so easy. One way to fix it, to do it properly, is to engineer the threshold in your data collection in. So you may have a counter of slow requests. So in your code, you say, if this took longer than 100 millisecond, increment this counter. And you can draw it, and then you can do the math here and saying, OK, 9% were off, so like my latency SLO didn't work out. However, if you have these histograms, they can just like aggregate the histogram, get the full distribution over a month. You have like 14 million values in here, and then you just read it off from the histogram. So if you have this kind of histogram power, latency SLOs get very easy to engineer, because not only can you accurately measure it, but you can also do the full experiment scale and see, if I would go a little bit further up or down, like how would my SLOs change. So if you want to engineer SLOs over past data, then this is, in my view, the best way to do it. OK, have 5 minutes to talk about sampling. So this is the new part about this presentation that I have not presented anywhere else. We looked into sampling at Zalando very intensively over the past few months because we wanted to save costs. I think everybody wants to save costs. We push sometimes 10 million traces per second to our tracing systems, which is quite a bit. So it's also quite expensive. So we were looking into ways to reduce the cost, and sampling is the first thing that comes to mind. And it's great for this kind of presentation because sampling involves a lot of statistics. So it's like, let's talk about this. And yeah, the basic trade-off is like by throwing away data, you decrease the accuracy, but you are saving costs. And the basic game that is always played is you have this big blob of telemetry data, which is meant to represent a lot of data. And then you are trying to do some statistics on it, like request rate, error, and latency. These are maybe the most important ones. And now the trick with the sampling is you actually forget most of it. So you subsample, so you get a much smaller blob of telemetry data, which is hopefully cheaper. But then you don't really know the precise statistic, but you do some estimations on it. And this is one example how this should look like. The interesting observation here is that this is readily available for simulations. You can very easily just play around with it. So in this case, we start with 100 values. Then, for example, we take 10% sampling. So for every of these values, we are flipping a coin in the simplest sampling model. Then unfair coin that has heads with 10% probability and tail with 90% probability. And then we retain around 10 values we don't really know. But if we want to get the original count, we have to take this estimate. We may have gotten 9, we may have gotten 15, and then we 10x that estimate and say, here, we should get around this number. And if you are doing this experiments that I alluded to, you can just do that 10,000 times. And then this is what happens. You kind of start with this distribution. So to have it on this equal footing, I just made this very silly-looking histogram. So this was kind of the single value that you started with. You know you had 100 values. And then you do the sampling, and then you get, oh, this actually looks very nice. This is actually almost a normal distribution. So this is what is called a binomial distribution, discrete version of the normal distribution. And then you multiply it up by 10 in this case and get kind of a scaled up binomial distribution. And then, you can calculate the error. So you will get around 10 values, and the expected error is 30%. And this is how it actually looks in the graphs. So if you start with a request rate graphs with 100 requests per second, so this is where it's attained here. If you are applying this game of sampling, you may actually get one of those green lines. And this kind of, by drawing it over it, you kind of get a sense how much wiggle room there is. If you quantify it, it's around 30%. That was that number. So how does that change with the request rate? Starting with 1,000 RPM, well, there's actually less error. That's great. If you get lower with the RPM, then it's like, OK, it's pretty shit. It's like 94%. And it turns out that in expectation, you only retain one value after the sampling. So the thing we learn here is that this is the number to watch out for. If this guy is still something you have in the middle, then you have a chance. But this gets too low, then you have really problems with the accuracy. And here is the only formula I left in the presentation, because maybe you have some utility for it. You can work out the math for the simple Bernoulli sampling of the count. And it turns out, you have a random variable following a binomial distribution, and the expected value is n. So we get the original value back in expectation. And the error is 1 minus p divided by n times p. And I want you to pay attention about this n times p. N times p is exactly the number of values you're expecting to retain. And it's in the denominator of this formula. And it means if this gets low, this gets large. So the heuristic is if you retain little values, then a lot of error is introduced. And that is important because you may not actually be looking just at the global request rate. You may be looking at slices from that. So maybe you are just looking for a certain user ID or some very specific parts of your data set. There, the counts after sampling can get very low, and you can get high error rates. We have a number of what we call critical business operations, where we're looking at what failure rate of password resets or something. They don't get 100 RPS. For those kind of applications, the sampling rate is really important. You want to retain more samples. And depending on your tools, you may have ways to steer the sampling rate for these cases or not. Certainly a capability we want to get. So I only talked about counts. I won't want to have more time to go into more details about other kinds of aggregates, just some examples here with percentiles. So here you get, after 90% sampling, a 36% error for a P90. So it's a P90. And you get a lot more error if you look at the P95. So that's another phenomenon. You are only having 100 values left, and then you're taking a P95. So you have only 5 values which are on the higher end of that P95. If that value gets low, if I would even go to a P99, then I cannot expect to gain a lot of accuracy. So that's also a practical tip. If you are making a release and want to see some latency improvements, make sure after sampling that you have enough data points to really have any accuracy in that percentile you're looking at. So particular high percentiles are susceptible to errors for this to a large degree. And yeah, I just like overlaid that. So it can be quite okay, it can be pretty crazy. Okay, so takeaways, effective way to trade cross with accuracy gives you sampling. Accuracy loss depends on the sample size and other factors. Unfortunately, it's actually a little bit complicated. There's no easy formula. I gave you one, but this is only for the counts. We have not talked about error rates. This is more complicated. Not talked about latency. That's actually very complicated. But the good thing is simulation gives you an effective tool to study this. And here's kind of the last giveaway. When we studied this, I made this calculator app, which you have if you go to heinrichhartmann.com/sampling, which is interactive and just allows you to play with all of these numbers. So you can put in like 10% sampling, 100 RPM, and yet this will actually run simulations in JavaScript and give you theory values and simulated values for error rates, request rates, and percentiles. It's not great software, so if you're accepting pull requests here, actually, there's lots of bugs, but it's like engineered to a degree that it's allowed for us to be effective. So if you want to have a crack at that, or just check it out, be my guest. And again, you will probably find lots of bugs, so if you want to fix them, please go ahead. But with that, thank you all for your attention. I have the source code for this stuff available on GitHub. The data sets, if you want to play around with the Python version of that. And if you want to stay up to date with more statistical content, you can subscribe to my Twitter. Thank you.